Hello, everybody. I didn't expect anybody to be here today, frankly. So I'm very happy that everybody showed up, and even more than last lecture. This is really great. I'm looking forward to a nice chat and nice semester talking about parallel C++ in various ways. Last time I asked around who had some C++ experience, and I got a few hands. And some people said they never did anything with C++. Just to bring everybody on the same page, I would like to kind of introduce or squeeze in one lecture that introduces at least some absolute basics about C++. So for those of you who know C++ very well, it might be repetitive, or you might already know everything. So please don't run away just because of that. It will get very quickly more advanced and more interesting starting next lecture. Okay. The other thing I want to do today is to take a moment to talk about Git and GitHub, because those are the tools that you will use to submit your homework assignments. On the other hand, it's not only a tool necessary for the assignments, it's a tool absolutely necessary for any software developer out there today. So if you go to industry afterwards or go to an interview in the industry, they might just ask you, hey, do you know Git? Or do you know any source code control system? And if you say, I've never done that, or I'm not too familiar with it, they might just send you away. Because almost all of the industry, at least all of those companies that take software development seriously, just assume that you know how to use Git and source code control systems. On the other hand, it's never been taught explicitly in class, at least here at LSU, as far as I know. So what I would like to achieve by forcing you to use Git for the assignments is to give you an additional piece of knowledge on the side that might be useful for your future career. And that's why for those who never have done anything with Git before, in the beginning of this lecture, about half an hour, a quick introduction what it is, why do we use it, what's this all about, and that might give you some introduction and some pointers where you can go and read more if you're interested. Okay, so let's go on with that. Git and GitHub. Git is the tool and GitHub is a web page. And I will try to explain what's what. So Git and GitHub are common tools that used in programming almost everywhere nowadays. It's kind of the source code control system that has established itself as a main means of managing source code across the industry. It was originally developed 20 years ago by Linus Torvald, the guy that also has come up with Linux in the beginning. It's freely available, it's open source. It's available essentially on all platforms out there, be it Windows, Linux, Mac, anything. So you can use it everywhere. The goal of Git is to track changes of your source files over time. It stores all the changes in a distributed database. Distributed in the sense that there is not one copy of a database everybody is communicating with, but there is a multitude of copies of the same database. And you as a developer are responsible to make sure that these databases are consistent. So you can download changes from another database to your local copy of the Git repository, or you can upload changes from your repository to any distributed or online Git repository. And that is a means of communicating with developers, right? When you have several people working on the same thing, then you have one central repository. Everybody is updating with their own changes. And it gives you means of communicating with everybody else. GitHub, on the other hand, is a web-based service provided by the GitHub company, nowadays owned by Microsoft. It's one of the largest online source code management environments that are available. They claim they have several 100 million developers working on with that web base. Anybody here has a GitHub account already? Most of you? Well, all of you, actually. Good. Because you will need it for your assignments. That's where the assignments will go and where you will commit your changes, where you will submit your assignments, where the autograder will run, and where I will go and will grade the assignments in the end. So GitHub is a web-based service that is built on top of Git. Git is that command line tool that can run on any platform. And they have built a very nice user interface on top of Git that allows you not only to manage source history, but it allows you to do compare versions of the software. It allows you to do code reviews. They have additional means of issue tracking and so on and so on. So many things, very nice and convenient user interface. We will use VS Code, Visual Studio Code, or I suggest that you use Visual Studio Code for your assignments. You can certainly choose your tool. If you are familiar with some other tools and you think that you're better off with some other tools, go ahead, do it. But I would suggest that you use Visual Studio Code. But as many other tools available, Visual Studio Code is very well integrated with Git. And in the end, you don't even have to type any command lines. It's just point and click, and you can work with GitHub through Visual Studio Code. As I said, many companies require new hires to know about Git, so it's a good thing for you to get familiar with it and to train yourself to be able to use Git to your advantage. You can set things up easily. Just download and install Git if you don't have it on your machine. In the context of this course, I will provide you with Docker images. Docker is a virtual environment that you can either install on your local machine, and when you start Visual Studio Code, it will download that environment onto your machine, and you have essentially the same environment as everybody else. I have prepared that Docker image for you, and there is Git pre-installed, so you don't have to worry about that. The other option is that you work on GitHub Codespaces, another facility GitHub provides you with, which is a set of online services that give you essentially a fully integrated development environment based on Visual Studio Code. So all you need, in the end, if you don't want to install anything on your local machine, you can do that. Just go to GitHub Codespaces and do all the development there. Everything is described in the assignment description instructions, so you will find the information there. And GitHub Codespaces will use the very same Docker file, Docker image, for you and create exactly the same environment you would have on local machine as well. The only thing you might have to do once you open Visual Studio Code once for the first time, you might have to type in these additional commands on the terminal inside Visual Studio Code to set up your local version of the local copy of Git and connect it to GitHub. The important part here is that you use the same email address as you've been using when creating your GitHub account, because that one is used to establish the connection with the GitHub service, which you will need for the homework. The other thing you will come across is GitHub Classroom. It's another service provided by the GitHub guys. This is more a tool for me as an instructor because it allows me to set up assignments. And there is a link in the assignment instruction where it says click here to accept the assignments. And when you click on that link, it will bring you to the GitHub Classroom page where you accept the assignment, where they ask you to enter your name or to associate your name. And that will establish the connection between the GitHub Classroom database and your GitHub account. What it also will do, it will take the starter code I prepared for you in the assignment and clone it to your GitHub account. So you will have your own copy of the GitHub, of the starter code for the assignment. and all the assignment you will work with, or you submit all your work to your local copy on your GitHub account. And what I can do through GitHub Classroom is to see how many commits did you have, what are the testing results, and so on and so on. So it's a very nice tool for me as well to get some overview of how the assignments go. It also enables automatic grading, as I said. Whenever you commit your changes through Git to your local repository on your GitHub account, it automatically triggers an autograder that runs somewhere on the cloud, and that autograder will run all the tests that will prove that your assignment is successful, or all the tests pass. So it will also enable individual feedback to each student. So I will add comments to your work. I will do the grading of your work on your GitHub repository and so on. So let's talk about version control in general. Any questions about this so far? Well, it's kind of straightforward. One thing I have to note, and we will get back to that over and over again. Well, there are two things, two advice I would like to give you. One is, if you work with GitHub Codespaces on your assignments, please note that these Codespace instances expire after 2 hours of idleness. So if you go away from your terminal just to grab a beer or something like that, then it will close the GitHub Codespaces instance if you don't do anything for 2 hours. And that means that the work you have done is lost. So never leave your terminal open just in GitHub Codespaces because you think you can get back to it. Before you leave it, always commit and push your changes to your local GitHub repository, to your GitHub account, and then your changes are being saved. That's one thing. I had students complaining to me that, hey, I've invested so much time and then I just went off for, I don't know, and then I came back and my work was gone. Yeah. Please always commit your work. It's the same thing like when you're typing some document in Word or in other editors, you usually save your work, right, when you leave. So it's absolutely the same thing. The other advice, Visual Studio Code has a bug which literally bugs me for years. Namely, when you commit your changes through Visual Studio Code, usually you are asked to supply what's called a commit message. It's a short textual description of what this change is all about. And if you don't supply that commit message in Visual Studio Code, it will go into an infinite loop and will just hang. And the only way out of that is to close Visual Studio Code and reopen it, which might, on GitHub Codespaces, create again the issue that you might lose work. So be very careful and at least type something into the GitHub, into the Git commit message before you click commit, just to avoid that. It's not my fault. It's just that we ran into that over and over again, and I want to warn you about that. Okay, version control. Just a bit more general, not just Git, but in general, version control is a database that keeps track of all changes to the files over time. So it allows for collaborative development because it goes into the same database eventually, and it allows to track who made what changes and when. It also allows you to go back in time and say, yesterday it worked, today it doesn't work anymore. What did change? Who broke the code? So you can look at the history of the changes and can even go back in time and say, okay, let's go back here and retry again, or things like that. Git is a distributed version of a control system, of a version control system. Not all version control systems are distributed. Others, like Subversion, or there was an early source code control system that was called CVS. Has nothing to do with the CVS shop. It's just called that way for whatever reason. And that database holds the entire code and history there. Since it's a distributed environment and you have a local copy of that database on your machine, You can even work without internet access. You can commit things to your local version of the database locally without internet access. You certainly can't talk to the remote copy of the database in that case. As I said, Git is one of the most widely used version control systems today. Okay, so how does Git work? There are a couple of concepts I would like to introduce because they are necessary to understand what Git is and how Git works. The first concept is, and that's the most important one, is a snapshot. Everything in Git is based on snapshots. Essentially, all the history is based on snapshots of the version of the file over time. A snapshot describes the state of all the files in the project at any given point in time. And that allows you to build that timeline of changes and allows you to go back and things like that. However, these snapshots are not created automatically. So you have to decide when you actually want to create a snapshot. And you usually create a snapshot whenever you feel that you have kind of accomplished something. Some people create a snapshot every 5 minutes. I mean, that wouldn't be a problem either. The other concept is called a commit. And commit is a process of creating a snapshot. And we will not seldomly talk about snapshots. We will most likely talk about commits. A commit is really a snapshot taken by you at a certain point in time. Every project is obviously made of many, many commits. And the list of commits defines the timelines of changes of all the files. Every commit has 3 pieces of information in it. It has a reference to the parent commit, to the previous commit on that timeline. It has a list of changes since that previous commit. And it has an associated hash. And that hash is something like that hexadecimal number I'm showing here. And these hexadecimal numbers are unique worldwide across all databases. So every commit has an absolutely unique identifier you can use to refer to it. Git doesn't store the whole file in a commit, but Git will only store the changes, the line changes that have happened since the parent commit. So if all you did was changing one character, the commit itself will store only the delta between the previous one and the current version of the file. The other concept is repositories. I already mentioned that. So the repository is that database. It's a collection of all files with their history, with their commits. It's the place where all the work is being stored. It can live on a local machine. It can live in a cloud somewhere. The act of downloading things from a remote repository to your local machine is called pulling commits. And the opposite is when you upload something from your local machine to the remote database, it's called pushing. Git is well known and loved by many developers because of the branching technology they have introduced. And the branch is a sequence of commits that are kind of interrelated. All commits live on a branch, and each branch is a sequence of commits. The trick is that there can be many, many branches at the same time. And that feature is used to allow for many people to work on the same code base. Because if everybody works on its own branch, on its own sequence of commits, there will be no interaction between them, and the work of one person can't directly influence the work of another person. Only later on, once you have finished your work on your branch, Git helps you to merge the changes from several branches and helps you to resolve conflicts. If 2 people have edited the same line in a file, then there is a conflict because the system will not know which of the 2 versions to use. But as long as the changes are not on the same line, Git will be able to merge these changes automatically. The main branch is often called main or master. And here is an example of how that looks like. So we have a sequence of commits, and every commit refers to the parent. That one refers to its parent. That one refers to its parent. And over time, we get that sequence of commits, which is a branch. In this case, it's a master branch. The top of master, the latest commit on master, is by default called head. So you can always refer to the latest version of the software using the head label. So when you branch of master, we see something like this. We have one commit where somebody has worked on that main branch and has committed C4. But before C4 was actually pushed, somebody else has created a branch of the same point and started to do their own work. And branches have their own unique name. So as soon as you create a branch, you're asked to specify a name. And from that point on, you can refer to the whole sequence of changes using this name. Later on, when you're done with developing your features, you can merge your changes back into the original master branch, at which point a new commit is created, which will contain the changes from your work and will integrate everything with the changes that have happened before, in the meantime, on the other branch. As I said, this is a perfect means of creating new features, right? When you want to create a new feature or want to fix a bug or want to do some performance work on some software system, you never want to directly add your changes to the master branch, because in that case, you might just break the product. Master is kind of the version that is used to sell to the customer. And it would be way too dangerous to allow everybody to just commit things to the master branch, because the chances that this would break your product would be very high. And for that reason, people create a branch, do the development on the branch, then they do exhaustive testing on that branch before they merge things into master. Also, at this point, very often some code reviews happening. So more senior developers than you are will look at your changes, at your change set, or at what you suggest that is to be merged, and will comment on it, will tell you, yeah, this is fine, but here, please go in and change something. This doesn't conform to some standard we have or whatever, or here's a problem in your code, and so on. And that allows you to keep working until everybody's happy. And when everybody's happy, you merge it finally back to master, which gives you a new version that you can send off to the client. Another thing in Git, and that is a bit confusing sometimes, is that a file can live in certain goes through different phases before it ends up in the database. Because you have your files on the working directory. When you're editing your file and you're working on it, then it lives only on the working directory. It's not in the repository yet. In order to get it into a repository and to commit it, you have to do two things. A, you have to stage the files you want to commit, and then you have to do the commit itself. Staging, if you use a command line, is done with git add, and committing is done with git commit. Add stages all the files you want to add to the commit, kind of lists the things you want to add to the snapshot, and commit is doing the actual committing. Now, in Visual Studio Code, these two things are one command. So you don't have to do both things separately. When you do a commit, it will automatically add all changes you have so far to your snapshot. So just to show that a bit more schematically, you have your changes on the working directory, then you stage your changes into the local database, and only then you actually do the commit. And when you do that, a new commit is created, and head of master is updated to point to the latest version of the master branch in this case. There are plenty of additional resources about Git available. Git, as I said, is used by millions of people worldwide, which means that there's plenty of information available on the web if you have any questions. Sometimes it's tricky, especially when you done something to your local database and you feel that you destroyed everything. In those cases, please get in contact. Nothing is ever lost with Git. It's just might be difficult to recover. So we can help you with finding older versions or things like that if you believe that, oh my God, all my work is gone. Don't delete the local database, ever. Just get in contact and we can try to recover things. And by the way, Shreyas is today here. He is a TA and he knows exactly how to do all of that. So you can always go to him and blame him if it doesn't work, okay? So don't blame me for this. It's his fault in the end. Okay, one last note about that. GitHub has introduced another term which is not part of the terminology of the original Git. It's called pull request. A pull request on GitHub is when you do work and you create some changes and you would like for those changes to be merged into master. Then you push your branch to the remote repository, and on the website you can create what's called a pull request, which tells the developers, hey, here is some change set I would like you to pull into master. And that's why it's called pull request. It requests them to pull your changes over. And these pull requests are there because they, on GitHub, the developers, the people that do the code review can go and look at your changes, can see what you have changed, can comment on them, and so on and so on. So you can go back and forth on the pull requests and do some fixing or changing or adaptation as needed. GitHub Classroom will create a pull request on your repository. That pull request is called feedback. And that pull request will have all the changes that you make to your repository in them. It's a means for me to see what you have changed in your assignment. So please don't close that pull request. Don't merge it. The pull request explicitly says, please don't merge that. I have tens of students who regularly merge that thing and close it. And you make my life more difficult if you do that, because I have to recreate that pull request manually for me to see what have you actually changed. So please never merge or close that feedback pull request that GitHub Classroom is creating on your repository. It's harmless. You can just leave it alone. Nothing happens if you don't merge that. Okay, any questions about that so far? Good. Then I'll switch over to the C++ slide set. Give me 1 second. Okay. So far about Git. If you ever have any questions about Git or if you need help with that, just please get in contact. We can certainly help with that. I know it's crucial for you to get that right, because otherwise your assignments will not get submitted. On the other hand, it's nice for me to force you to do that, as I said, because that forces you to really embrace the Git technology, and that will help you in your future career tremendously. Even if you don't believe that this is something you want to know. When Git came up 10 years, 15 years ago, I hated it, frankly, because I was used to another source code control system, and I couldn't get used to it for whatever personal reasons. But once I got over that hurdle, I really start appreciating the system because it helps you to organize software development in a proper way. It helps you enforcing certain software development practices that are consistent across a particular software project. So I think it's one of those tools everybody who is serious about software development should know and should be able to use. I will not grade you about that, right? I will not ask you any questions about Git ever, but I will expect that you use Git to submit your homework. Okay. The second thing I wanted to do today is to talk about some very basic C++ things that I believe are important. And again, if you have done C++ before, that might be nothing new for you. You might say, oh, okay, I know all of that. So please, in that case, bear with me. Next lecture will get much more interesting and much more advanced. Just as a glimpse into next lecture, what I want to do is to develop some custom types in C++ that allow us to automatically count operations. That is good for performance measurements because you want to know how many operations has that code actually performed. Something which might be very difficult to figure out. If you have a complex algorithm, you might not be able to follow that properly or do it by hand. So you can instrument the code with some fairly simple C++ class, and it will tell you in the end, hey, I've copied that object so many times. I have done comparison with other instances of that same type so many times. And what we will do next class is, remember in the first class, we discussed in the very end how to find the number of unique elements in an array. And we had two options, using a set and using the unique algorithm. And I will show to you, just to motivate you to come next time again, right? I will show to you some very interesting insights and will prove to you that I was right when I said the version that is based on the unique algorithm is much faster. And we will use that class that I will develop, that type that I will develop next lecture for that. Okay, enough. Okay, so we want to write a program in C++. The first thing that comes to mind, we want to achieve high performance. That's probably the reason why people come from Python or from other languages. They say, okay, I have to use C++. It's because I need more performance out of my code. Which immediately means, okay, I need better performance, so I have to be able to measure and tune a program. Which means I have to actually run it. Which again means I have to actually compile it before that. And last but not least, I have to write it. I have to write the code. I have to make it work. So that's why C++, and we will use Ubuntu as the operating system in our Docker image. That's why all that class is today will be about C++. And you can think about it like the Russian dolls, right? The deeper you get, the more interesting things get. My granddaughter loves playing with these things. She really enjoys putting things in there, and so I hope you will enjoy that as well. Okay. If we start from the general premise that the computer should be a labor-saving device, what is necessary for that? Well, you can use a computer to increase the amount of work you have to do. I remember a time at LSU when the Workday system was introduced. Nowadays, the Workday student system will be introduced, so everybody of you will get in contact with that as well. Workday is a system that manages business processes. And when that system was introduced and we all moved from the paper-based business process of filling out a form when you wanted to go on a business travel to the Workday-based where you fill out the form online, we had to do both. We had to fill out the form had to be scanned in and had to be added to the form that I had to fill out, you know, very interesting thing. And we had to scan the form because the signature had to be on the form, and the signature. And just to avoid these things, we want to build a environment where the computer can be used as a labor-saving device, and that especially includes mental labor. So what we want to do, we want to use productivity tools, and I really suggest that you use VS Code for that. It's a very nice integrated environment that allows you to edit code, to talk to GitHub, onto Git, to run code, to connect to Docker images. So it's a very, very sophisticated and nice environment where we can do all the things we want to do. As said, There are many other options for that. You might have your favorite environment already, Eclipse, whatever. Everything is doable in any of those environments. And if you are feeling more comfortable to use another tool, be my guest. I just can't, I may not be able to help you with that because I may not be familiar with the tool you're choosing. So Eclipse is a kind of integrated development environment. And the most important thing actually is that it includes all the tools you will need in one surface and one user interface. And it has a version that will run completely on the web. In the Codebases instances, you will get a Visual Studio Code user interface or something that looks exactly like the Visual Studio Code interface, but it will not run on your local machine. It will run in your web browser and will connect to the cloud resource you're running your stuff on, which is just great because you can move around and you can work either locally or there, and the code is shared through the Git database where your changes live. Yeah, as I already said, I suggest that you use VS Code, and we will provide you with a Docker image that gives you an environment you can use for your assignments, for your experimentation. And that Docker image will guarantee that everybody looks at the same environment. So you don't have to install any additional tools in theory. The assignments the assignment instructions have all the information I hope you need to set that up for yourself. The other thing we might come across is shells. Who has worked with Linux before? Okay, some of you. Some Windows users here? Mac users? Yeah. You will have to get used to Linux because inside the Docker environment, we will have a Linux installation. So all the work will be done inside Docker on a Linux. But Docker itself runs on Windows just fine. That's not a problem. You can install the Docker client on your Windows laptop and run the Docker image, download the Docker image there and run it. The main command line in Linux is based on shells, and there is a history of shells: Burn shell, Corn shell, C shell. The predefined shell in the Docker image will be bash. By the way, anybody knows what bash stands for?
It's the born again shell.
Yeah, born again shell, right. So that guy wasn't happy with the original shell, so he wrote the thing and improved it and called it bash. It's burn again shell, right? Or born, I don't know how you pronounce it. It's derived from that name, yeah. So you can think of it as born again or burn again or whatever, you know. Okay, so all these shells are read evaluation execution loops. So it's a command line where you type things that causes some other processes to be started, and it comes back to your user interface so you can do the next thing. But it has also a complete scripting language. So if you're interested in investigating that, feel free. Okay, so far so good. That's for the environment. Now, we have a program, in this case a small C program or C++ program. What do we need to do to get it on the computer, to make it work? Well, there could be some magic involved, right? Then a miracle occurs, poof, and things start randomly working. But there is some logic to the madness. There's a scheme behind it, and I will try to introduce you to that. If you're a Python user, you exactly know what this code does, right? It imports the mass library, then it defines two variables, takes the square root of the first variable, assigns it to the next one, and prints it out. When you work with Python, you work with a so-called interpreted language. It's a language that doesn't require any additional steps to be turned into something that is doing the useful stuff. And that interpreter that is doing that is the Python executable. So you usually type Python, then you give the script name, and it will do what you want. So it's immediately interpreting the code line by line. Well, nowadays, under the hood, it's doing some compilation internally just to speed up the whole process, but the idea is still the same. You have a very interactive, very rapid development environment where you can just try out things and get response right away. When you have a compiled language like C++ or C or other compiled languages, this is a bit more complicated. You have to jump through more hoops before you can actually run the code, before something happens. So if you take your program, you have to first turn that into a language that, or into some representation the computer can understand, which is some binary code, which is just a bit pattern, a bunch of bits. And those bits are generated in a way so that the hardware, when it sees those bits, can do what you actually wanted it to do. So we have to first convert it into some assembly code, then, which is another language, essentially. Then this gets converted into some object code, which is yet another language, which is a binary bit representation. And only that can be converted into the actual executable that you then can run on your machine. If you compare these two representations of Python and C++, you will see that there's a lot of similarities, but there are also some differences. The main difference is, well, one of the differences is that you can't have code outside of a function in C++. In Python, you just put it there. You can put it in a function, you don't have to. In C++, all executable code has to be in a function. In this case, it's the main function. And the function starts with a function definition, or the name of the function, the parameters. In this case, there are no parameters to main, and a return value. So we have to specify what type has this thing this function actually produces. In this case, it's an integer. Then the code is inside a pair of curly braces, which marks the body of the function. Curly braces are very important in C++. Well, they look fancy, but they also are very important because they give you a scope. And scoping is one of the important features of C++ because scoping defines the lifetime of variables. In this case, the variable A and B live only until the code reaches the end of the scope they were defined in. Outside of that scope, variable A and B are not defined, not available, and can't be used for anything. You can put variables in the global scope, as we will see on next slides, and those variables live until the end of the program, until the program exits. Also, instead of the import statement, in this case, which makes the math library in Python available, we have to use hash include statements in C++ that are very similar in conceptually. Under the hood, they do something completely different, but you can think of them as making things available to your code in the same way as import math makes the math implementation available to your Python code. I think it's self-explanatory what this code does. You define two variables, you take the square root of one, and then you print the variable to the console in a very Pythonic syntax by specifying the placeholder, and all the placeholders in that string here will be replaced by the corresponding argument that comes after. Very similar to what Python actually does. The last but not least is a return statement, which is the place where you specify what should that function produce. And since main is the function that is run first when your code starts, just by definition, it is supposed to return an integer. Where does it return the integer to? It returns the integer to the operating system. It allows you in the operating system to check what has a executable I have run actually returned to me. And by convention, returning 0 from main means everything's okay. So if you want to return some error code or some flag that something went wrong, usually just return -1 or something, which that you can look at inside your shell whether things have gone right or not. So this code can't run, at least it can't directly execute. So we need to turn it into code that can actually run. We need to turn it into an executable. As I said, it's a multi-step process. We have to compile it to an object file, which are bits that correspond somehow encode what this code is supposed to do. And then we have to link it to the libraries that are made available through the include statements, and that in the end provide the bit code that has been pre-compiled for print, for square root, and so on. Just a couple examples how you can compile things on the command line if you really want to do that. The compiler is usually called C++, obviously. You just pass the file name you want to compile, and it will do everything, all the steps I mentioned in one go, and it will produce an executable. You might ask, what's the name of the executable that is created? Anybody? It's a.out on Linux, yeah. So the default name for the executable is a.out. If you do that, it will create a file which is called a.out, which has a binary, the linked executable. You can compile many of them on the same command line. You can force it to compile the C++ code to object code only by specifying -c, which means compile only. Here, an option is used that specifies the name of the generated file, so you can do the same thing for your executable, -o output name. Or you can create an executable from multiple object files you have created before, and then name the thing that has been, the name of the executable is my executable in that case. Last time I showed you that slide, essentially the same thing again, but a bit more depicted, so easier to understand perhaps and easier to follow. You have C++ code, which is fed to the C++ compiler. That generates compiler spits out object code. Then we have to use a linker, and the linker takes other pre-compiled object code that is installed on your machine by the system or operating system related stuff, C++ standard library, object code, and so on and so on. HBX will be linked that way in the course. And that produces an executable program where all the pieces that are necessary are combined in the same executable, in the same binary. There's a lot of information about that online. If you're interested more in learning more details, you will find that. Also, I said last time that this is very tedious because you don't want to type the command lines each time. It's annoying, especially if you have more than one C++ file. You don't want to type that every time when you want to compile. So what we will do, we will use CMake. CMake is a tool that generates a build system which essentially contains all the command lines for the compiler and for the linker and for the assembly as you need it. And so it's a very convenient tool because you generate the build system once, and then you can use that generated build system to build your executable with one command, which simplifies things a lot. The easiest way to, well, CMake is you can think of it as another language, as a scripting language in some way. So you have to describe to CMake, what is it I want to build? And you do that essentially with one command, which is in this case @executable. And that @executable says, please, I want to create an executable which is named demo1, which has to be compiled from demo1.cpp. And that's it. That's all what CMake needs to generate the appropriate command lines for the compiler, for the linker, for everything. So these three lines will be stored in a file that has to be called cmakelists.txt. I know the guy who came up with the convention. I hate him. I don't know why they chose that name, but this is the name that has established in CMake. And you will always come across these cmakelist.txt files. And if you see them, you know this is a file that CMake will use where you can describe to CMake what your build system has to look like. So we have two files in our directory. Then we invoke CMake on that directory. It will do some magic. It will generate the build system. And once the build system has been generated, all you have to do, you type make. Make is a tool from Linux which understands build systems, and CMake has generated a build system that Make understands. And as you see, make will go through all the steps automatically that are needed to build the executable. And once that's done, you can run your executable and you will get the result. So it's an easy way to simplify to work with compiled languages, which is a bit more complicated than interpreted languages. But I believe with CMake, it's fairly straightforward. It's not very difficult because whenever you make changes to your source files, all you have to do is make, and then you can run it. So it's a two-step process, which simplifies things a lot. If you have questions about CMake, there's plenty of resources available online, but we should be able to help you with that as well if you want to set that up. All the assignments will have a CMake file predefined for you, so you don't have to do anything about that. VS Code knows about CMake, so it will automatically do the first step for you when you open a project in VS Code. And it even has a button where you can tell it to make certain executables only without even have to type make. You can do everything using point and click through the user interface. And there's some description of that on the course website, so you can go there and see how that's done. But again, VS Code has a very extensive documentation. You can find all that information online if you ever have to. Okay, C++ is a giant language. It's an incredibly complicated, large language that has grown over the years. Essentially has grown since 1970s, somewhere in the 70s. And the interesting thing is that the stuff people have written in C++ in the 70s, 1970s, you can still feed to a C++ compiler today, largely. There might be details, but at least after the first standardization round in 98? C++ 98 was first standardized C++. That code from C++ 98 definitely works today on every C++ compiler. So it's a language that is well described, well standardized, and well supported by the compilers, and has gone over a long period of evolution, but it's still fully backwards compatible to what it was in 1998. We will focus on C++23, which is the latest version of C++ available. They release a new version of C++ every 3 years nowadays. So that's why you might see 14, 17, 20 mentioned here or there. But essentially everything that is defined in C++23 is available to us. But we will take a very small slice of C++ and we'll use that for our needs, which will make the language, as I said, almost Pythonic. It's a very nice way to write code that is very readable and very nicely understandable. So we will use very modern features from C++, and we will avoid legacy features such as pointers. I hope I'm right, but you will not see me using a single pointer in this code, in this class. So if you're here because you want to learn about pointers, come to my operating system class. There we have to talk about these things. But here in this class, we will not use pointers because pointers are evil, at least from a certain perspective. And we don't do object orientation in the classical sense, that we don't have large hierarchies of types and things like that. This is not needed for what we need. We will create a lot of types, new types ourselves, but these types are usually have a very flat hierarchy. So they might be derived from one other class for various reasons. But we will not have virtual functions. We will not have all these object-oriented features that the Java people are so proud of. Okay. Very quickly again, hello world, include statement makes the print function available. No arguments. Comments are everything that follows the doubles / or inside that classic C-style comment. Otherwise, I think it's self-explanatory. This is a string, which is very similar to Python when you know Python, so you shouldn't be surprised there. You can't use single quotes for strings in C++, so you always have to use the double quotes for strings. Otherwise, I have said all of that already. One important type and one of the differences to Python is that C++ is a typed language. In Python, you don't have type. Well, you have types, but a variable can change the type over time, right? You can assign a string to a variable, and then you make it a double, and then you make it something else. And Python is absolutely happy as long as you do the right operations on the thing that is currently being referred to by a variable. Python will let you do that. It will only complain if you have an integer there and you try to do a string operation or things like that. In C++, a variable always has a type, and that type doesn't change. So once you define a variable, you define it, what type does it have, and it can't change that type. You can't assign another type to it afterwards. The compiler will not compile the code. It will complain about that. It will tell you, hey, you're trying to assign an integer to a string. Is that what you want? Things like that. Variable definition, type, name of the variable. Very simple. We have many built-in types. There are 7 main built-in types. Anybody knows the 7 main built-in types in C++? Well, 3 of them are listed here. Integers, doubles, chars, floats, what else? Boolean, shorts, longs, this kind of thing. So it's a very basic set of built-in data types that can be used essentially for integer and for floating point operations. Everything else has to be built on based on user-defined types, like the standard string here. So string is a special class that is defined by the standard library. That's why it has that std : in front of it, which is a user-defined type. So all the things we will see, standard vector, standard string, all the things we will see from the standard library are defined using the features of C++ itself. So it's user-defined types that are predefined for your use. If you are a C programmer, you might write code this way. You might define all the variables in the beginning of a function, and then you assign the values to them later on. That's kind of the old days. What we want to do in C++ is to move the variable as close as possible to its first use. So don't define it in the beginning of the function, 500 variables, and then do your function. No, move the variables as close as possible to the block of code where it's needed, and always initialize the variables if possible. So never leave a variable uninitialized at the definition point, like here. What are the values of x and y before the assignment is happening? Anybody?
0.
No. What are the values of x and y before I assign anything to them? No. It's undefined. They have the value of the bits that happen to be in the place where the variables are being placed. So if there was some code before that was using that same region of memory for something completely different, and then you call a function and that function happens to place these variables in that space, they will inherit the values that are left over from the previous variables, which is complete nonsense and never what you want. And that is the reason why I suggest always initialize your variables to at least 0 explicitly, because that will avoid all these problems that might come from these uninitialized variables. So best practice, don't declare variables before they are needed, and always initialize them if possible. And we will talk about how to initialize user-defined types. And you will see that C++ has a very nice mechanism that allows us to guarantee that our variables are being initialized. What I want to do now is to talk about namespaces a bit, because that is an interesting thing. And you already have seen the std : annotation before a name in the code I used. And that is nothing else but a namespace. In C++, a namespace is a region of code where the variables have to be unique. And if you want to use the same variable name, you can't do that inside the same scoping, but you can define it in a different namespace. So it allows you to organize code into logical segments, like the std: is namespace standard. Everything in namespace standard is from the standard library. It prevents name collisions that can occur, especially when your code base includes multiple libraries. Right? You're pulling in code from a developer you don't even know. It's an open source library you pull in from somewhere. So how do you know that this guy hasn't used the same name as you want to use in your code? And that's why all modern C++ libraries are defined in their own namespace. That means that as long as nobody uses the same namespace name, there can't be any variable clashes, because the name is valid only inside that namespace. Just as an example, very simple, I want to print the value pi. So the compiler needs to resolve that symbol, right? I refer to pi. In this case, it's a global variable, so the compiler will be able to see it, because the global namespace is visible from everywhere. So now I move my variable pi into my own namespace. That means I have to refer to pi using the namespace name as well. Otherwise, the compiler wouldn't be able to find it, because by default, if that wasn't here, the compiler was looking in the global namespace only. So it can only look upwards in the namespace hierarchy, but it can't automatically look downwards. That's why if we tell it, hey, that pi is actually defined in our namespace, then it will find it and will work with it. The other way to do that is to use, if we have many things that we want to import from a namespace, we can use a using namespace directive, which tells the compiler that inside this scope, from this point on, all names that are defined in that namespace are available as if they were in the global namespace. Okay? So this will work. So you can hoist everything from one namespace into the current namespace. Last but not least, just to show you that you can disambiguate your variables by defining the same variable name but in different namespaces. Since I tell the compiler, hey, please hoist everything from the first namespace here, this will compile just fine. You certainly could just add the correct namespace qualification here. Nothing too surprising, but I would like to raise your attention to this, because we will use namespaces a lot. There will be the standard namespace, there will be the HPX namespace, there will be other namespaces we have to deal with. One of the libraries we will use for linear algebra is called Blaze, B-L-A-Z-E. It's another namespace we will use all the time. Hold on. This is something went wrong here. Okay. So how do we organize our programs? Since software development is very difficult, we have to find ways to simplify our own life. And if you think about it, what is computer science all about? Computer science is all about creating tools to manage abstractions. That is the big difference. That is the actual essence of computer science. So what kind of abstractions do we want to build? We want to build abstractions of code, and we want to build abstractions of data. And that's what we call data structures and algorithms. That's these things that make up our programs. So we will apply the same principles we apply in normal world when we want to grasp a problem, and then we start to take it apart and make it into smaller problems so that we can understand them. So we want to apply the same principles to software development. Just an example, since we are doing scientific computing here, so let's do a bit of scientific computing. Let's solve square root. We want to find the square root of a number. And the easiest way to do that, and we will talk about that in more detail later, is to use a method that relies on the fact that the value of a function at point x plus a very small delta x is roughly the same as the function of x plus delta x multiplied with the gradient at that point. So we can derive a simple rank 1 Taylor series which tells us that delta x is essentially defined as minus the value of x divided by the gradient of that function at that point. And that allows us to find the fx equals 0. That allows us to solve that equation. For instance, if we have an equation f of x is x squared minus y, in other words, y is equals x squared, and we want to solve that, then, well, y is the square root of x. So the derivative is 2x. In other words, our delta x is defined like x squared minus y over 2x. And this allows us to iteratively solve and find the square root, because we can apply that equation over and over again. We start with some value at some point, calculate the next value, and use whatever we get and insert it in the same equation again, and narrow down our solution to the solution we're interested in. We will do that using this equation in a minute. So if you look at some code which is doing that, essentially it's a for loop. In this case, I'm just doing 32 iterations because I want to limit the number of iterations somehow. I start with an arbitrary initial value 1. It's my guess. I guess my square root is actually equal to 1. And I calculate the delta x based on that formula I just had here, right? X squared minus y over 2x. Then I add that dx to my x, and that gives me the value of x, the next value in my iteration of my x. And if the absolute value of my delta is actually smaller than some epsilon, in this case 10 to the minus 9, then I think that I have reached a accuracy I'm happy with. And then x is actually my square root. And in the end, I print my square root. Okay? So you see how various language features here in this code. We see a for loop, which has 3 parts: from, to, and reinitialization. We see if statements, conditionals, very similar to Python, and a break statement, which stops at the point when we have reached the necessary precision and we exit the loop. Very straightforward code. Now, this is square root of 2. Let's compute square root of 3. What will change? What do I have to do in order to compute square root of 3 instead of 2? Well, the only thing that changes is this number, right? So it's a perfect candidate to create a function. So let's create a function out of it, where we move this function, or this code we had in the main, into its own function and give it an argument, y in this case, and just the very same code, and use that function instead of our constant value. I have added it in another namespace just for the sake of it. And then we can call that function with our 2, and we will get the result. So it's a very simple example how you can abstract code and move that into a reusable block of code, which is called a function, in this case, to calculate the square root. Just a very simple example on how functions can be defined. Now, in this case, we have one argument, a double, which is passed in as a parameter to the function invocation. C++ requires you to, the sequence of arguments has to match the sequence of arguments expected in the function, obviously. In Python, you have named arguments. So you can say something value equals to whatever. That's not available in C++. So you always have to specify the arguments in the right order and in the right amount in the right number of arguments. Now, let's change that code and assign x to y before we return. And then we print y here. What will it print? We call the function, and just as an experiment, we assign x to y in addition here. What will be the value of y here when I come back? 1, he says 2. What else will it be? Right, it calculates the square root and then assigns whatever it has calculated as square root to its argument. And then it prints the argument here in the main function. What will it print? I know you know the answer, so you don't have to say anything. And here, I mean, we have 2. Who is in favor of 2? Okay, at least some. It's 2. Why is it 2? Because C++ is a language that loves doing copies. And it always invokes functions using value semantics. All arguments are being passed by value. And that means that the value of y here will be copied into a new variable y there. And when you change that variable, obviously the original variable doesn't change. Yeah? So passed by value semantics. Everything not otherwise specified is passed by value. And that's one of the reasons why some people that come from other languages claim that C++ is slow. Because they start passing giant data structures to functions by value, which causes this giant data structure to be copied each time the function is being invoked, which costs a lot of time doing things. Okay, so what if we add an ampersand there? And that ampersand stands for this double is not now a reference. It's not a double anymore, but it refers to another variable. In other words, it refers to the very same variable like outside. So what will it print in this case?
It will print x value.
Well, it will print the square root of 2, right? Because we told it, hey, this is a reference. So that y and that y are the same variable, refer to the same location in memory. Absolutely identical. It's just 2 names for the same thing. And you can rename that one to XYZ or whatever. It wouldn't make a difference. The reference is an important part. This is something people struggle with because sometimes they forget that they have to change the place where the function is defined and not the place where the function is invoked in order to turn it into a reference. Okay? This is the important part. So the argument y was now passed by reference. It's called passed by reference. The function will operate on the original argument because both variables are the same. They refer to the same place in memory. So why would you want to do that? Well, there are several reasons. You might want to have an out parameter. You might want to return a value from the function back to where it was called. You might want to avoid the copy because you have a giant data structure you want to pass along and you want to make sure that the giant data structure is not being copied but referenced. By the way, there's also pass by const reference, which adds a const before the ampersand, which additionally gives the promise that the function will not change that variable. That's it. Sometimes it's very useful. So if you know that the function will not change what you pass in, but you still want to pass it by reference because of efficiency reasons, just declare it as const reference and that will do the trick. Okay? Okay. There's a bunch of core guidelines, C++ core guidelines. People have developed a whole set of suggestions how to use C++, what is good C++, what you should avoid in C++. It's called the C++ core guidelines. Here are some linked with regard to functions. So if you want to read about it, just go there. Any questions? Everything clear with C++? Everybody a perfect expert in C++ now? Great. So next time we will do more interesting things, and I hope that you will show up. Thank you so much for your attention.